Hello everybody, my name is Adam. Henry, Grayson, and I work together on this project. Our topic is chaos in cryptography, and this is our presentation. Our presentation includes the paper and the source that inspired our project. We have some introduction and background of some of the project materials. We have the results of our project implementation, and we have some future projects that could be explored. The paper that inspired our project was a paper called Color Image Encryption Using One-Time Keys and Coupled Chaotic Systems. This paper used chaotic dynamical systems to encrypt and decrypt images in a way that was very robust to encryption attacks. We're going to implement a similar project, but leave out a lot of the robustness to encryption attacks. So just a little bit of introduction or background into encryption. If we have some information or data that we want to securely communicate to one party, and we don't want any other party to be able to view or access that information, we want to encrypt that. So an initial way of going about that is by using math functions with random number generation to transform our original data or information. However, when we do this, we lose the original data, so this is not a correct way of going about it. A successful method for encrypting and decrypting information is by using coupled chaotic systems with what is called a driving and receiving system framework. So if we consider the Lorenz system, which is a 3D dynamical system that exhibits chaotic behavior, so we're going to set up two identical Lorenz systems such that the X component of the second system or the receiving system is equal to the X component of the driving system or the first system. This is what that looks like, where you have the driving system as a fully independent Lorenz system and the receiving system as a dependent Lorenz system dependent on the driving system, where you have the differential equations for the y and z components of the receiving system involving the x component of the driving system. So in order to see how the driving and receiving system framework can be used to encrypt and decrypt information, we first must talk about the topic of synchronization and coupled chaotic systems. So chaotic systems by definition exhibit sensitive dependence on initial conditions, where if you have two chaotic systems with different initial conditions, the solutions of those systems will diverge after some time. And we can briefly see this with an example of two identical Lorenz systems, where we set the initial conditions for all of the variables equal to 5, except for the x component of the second system, which we set to 5.0001. So by solving this using ODE45 and plotting it in MATLAB, we see that the two trajectories are very close to each other and indiscernible for very small values of t, and then as the solutions evolve over time, the two trajectories diverge from each other, and we can clearly see two solutions in the butterfly diagram. This is a plot of the trajectories of the components of the two systems over time. For small values of t between 0 and 15, we can see that the components of the two systems are almost equal to each other and indiscernible. And then after t equals 15, the two systems diverge, and we can see that clearly two systems are being plotted. And this is an example of sensitive dependence on initial conditions. So now if we attempt to replicate this with coupled chaotic systems using the driving and receiving system framework that was listed in the previous slide, we have that as we evolve both of the systems with different initial conditions, instead of the two solutions diverging after some time, the two solutions converge to the same solution after some time. And this is the opposite of sensitive dependence on initial conditions. The most general and minimal condition for synchronization for one-way coupling to occur is that the Lyapunov exponents of the response system must be negative. And we will now see this with an example of two coupled Lorenz systems where we set the initial conditions of the first system to be equal to 5 and the initial conditions of the second system to be equal to -5. So in terms of the setup of the two systems, this is what it looks like, including the initial conditions. And we're going to have that after some time, the solution of the receiving system converges to the solution of the driving system, and only one trajectory will be able to be discernible after that time. So solving this with ODE45 and again plotting it with MATLAB, we do see that the two trajectories start out as two completely distinct solutions, and then after some time, the two trajectories converge with one another, and only one trajectory is discernible in the butterfly diagram. This is a plot of the trajectories of the components of the two systems over time. The top plot shows for all of the t range. The bottom plot shows for just a small t range. The top plot, it looks like just shows one system, so it looks like the synchronization happens very quickly. So when we zoom in for the second plot to a small value of t between 0 and 3, we see that it's a very quick synchronization between y1 and y2 and z1 and z2.
Now, we've previously shown that the systems can become synchronized over a long period of time. And now we want to find out, how does that happen? Why does that happen? Why can the driving and receiving systems synchronize over a long time, even though they're both chaotic systems? So what we'll do is we will look at the driving and receiving systems, Lorentz systems like we've defined before. And we're going to look at and see, how can we prove that y2 will converge to y1, and then how will z2 converge to z1? And a good way we can do that is to create a whole new system where we'll take the difference of y2 and y1 and the difference of z2 and z1, and we'll show mathematically how this system construction will converge these two chaotic systems. So when we look at the system here, we set up the system with the driving equations and then a receiving, where we're sharing x1 and x2. There's going to be the same. So when we're sending over information, you're sending this x variable will be shared within the receiving system. So when we set up, we're going to show that these y2, y1, and then z2, z1 converge to the same values. So setting up these error variables here, where error in x is going to be the receiving minus the driving. It's x2 minus x1, and since it's shared, it's going to be 0. So as c approaches infinity, we'll have that ex is going to be going to 0. And we want to show that ey and ez have similar behavior. And so if we set up the differential equations for this, y2 minus y1 dot, and then ez dot will be the difference, z2 dot minus z1 dot. And so if we write these out, taking the y2 dot are x1 minus y2 minus x1 z2, and then subtracting our y1 dot, so we'll have r minus rx1 plus y1 plus x1 z1, and our x1 terms here are opposite, so we can cross those out, and then we will combine this minus y2 here, so minus y2 minus y1, and then we'll combine the x1 terms here, so we'll have actually minus x1 z2 minus z1, and then we can see here this y2 minus y1 z2 minus z1 are our error variables we defined. And so we can say that ey dot is going to be equal to minus ey minus, we'll call it x of t times ez. Doing the same with ez dot, we'll have z2 dot x1 y2 minus b z2 minus x1 y1 from z1 dot plus b z1. Then we'll group these terms here. x1 will be times y2 minus y1. And then we will group the b here, z2 minus z2 minus z1. And then we also have the similar construction here going on. So we'll have ez dot is equal to x of t times EY minus BEZ. So we have a two equation system of differential equations here, and we want to show that these two, EY and EZ, are going to be converging for t going to infinity. One way we could do this is with a Lyapunov function v of EY, EZ, and we can if there exists Lyapunov function, this one way we can show that EY and EZ are going to converge. And so what we can do is group this left-hand side. Since we have two variables, maybe we can get a product rule on this side by multiplying the top equation by EY, the bottom by EZ, and then adding them together. So EY dot plus EZ dot. So this is a form of the product rule. And so let's see what happens to our right-hand side. So we'll have minus EY squared minus x of t EY EZ, and then plus this equation here. So plus x of t EY EZ minus b EZ squared. And so these two middle terms, x of t EY EZ, x of t EY EZ, are equal and opposite. Those will cancel out. We'll be left with minus EY squared plus EZ squared. And we can show this left-hand side here, since it'll be the product rule, the derivative product rule with respect to time, with the dot denoting a derivative with respect to time. It's going to be EY squared plus EZ squared ddt. And we can call this here our v, our Lyapunov function. So EY, it's a function of EY and Z. And the good thing about this is it's a positive definite function. It is greater than 0, strictly greater than 0. Well, not strictly, I guess, if it's 0. This is greater than 0 for all EY and EZ. And then the derivative here is, from here we took the derivative of our v here. You can consider it this right-hand side. So this is v dot, which is negative EY squared plus EZ squared. And our v dot, no matter what EY and EZ is, positive or negative, v dot will be always, v dot is always less than 0 for all EY and EZ. And since these conditions are satisfied, so v in fact is Lyapunov function, and that shows that we get convergence for EY and EZ as t goes to infinity. And so we can indeed use an x of t variable as our x as our driving variable in order to get y2 to converge and z2 to converge with y1 and z1 and synchronize these two systems. Now we're going to look at some alternate scenarios and see whether we can use y or z as our driving signals in our chaotic systems. And of course we can use them, but we want to know if they'll converge, whether we can get a convergence of our other state variables. So one scenario we'll look at is y of t, y1 equals y2, and we'll be sharing y among the two systems, the two chaotic systems. And so when we take the error system involved with this scenario, we have E dot sub x is equal to negative sigma E sub x. EY will be 0 because y2 minus y1 will be 0. And then E sub z dot will be equal to y of t E sub x minus b E sub z. And we can see that this gives us a system where The E sub x is decoupled. There are no other variables in that differential equation, so we can solve that one directly just by separation of variables, and we'll see that E sub x exponentially decays towards 0 over time, and so we will get a convergence on the x variable with this system, which is good. And one way we can look at the E sub z dot equation is that over a long period of time, we know now that the E sub x, the error in x, is going to converge to 0 over a long period of time, so that nonlinear term y of t multiplied with E sub x is going to disappear over a long period of time as E sub x converges to 0. And then we'll have a sort of decoupled system also, where E sub z dot is going to be only dependent on E sub z at a long period of time. And we can show that it's similar to the E sub x case, so E sub z is going to converge to 0 exponentially, but with b in the exponent. And since we're looking at sigma and b as strictly greater than 0, we know, okay, that E sub x and E sub z are going to converge. And so that confirms y of t can be used as a driving signal. Now we can look at and see, well, can z be used as a driving variable? And it comes up with a messier system of equations, and also a system of equations that looks just like the Lorentz system. As you can see, the E sub x dot, this is the x dot part of the Lorentz system, and then the same with the y. The only thing we're missing is the z, but that hurts us because now we have two equations here and three variables, and it's very hard for us to solve this. And so there are no solutions that show that these systems are going to converge. So E sub x and E sub y are not going to converge. This leads us to the conclusion that Z cannot be used to synchronize two chaotic systems. Now we're going to take a look at examples of how this can be used to encrypt and decrypt signals.
Synchronization in coupled chaotic systems can be used to encrypt communications, such as audio. If an information signal S of t is desired to be encrypted and communicated this way, the sender generates a chaotic signal x sub d of t using data from the driving chaotic system. We then sum the signals S of t and x sub d of t and send that as an encrypted signal. This can be denoted S of t plus x sub d of t. After receiving this encrypted signal, the receiver can then synchronize the receiving chaotic system through the use of data from the encrypted signal and produce the chaotic signal x sub r of t. This chaotic signal can then be subtracted from the encrypted signal to approximately recover the information signal S of t. The convergence of the synchronization is time dependent, so there is a small inherent error in the recovered signal. An example of this would be distorted audio at the very beginning of an audio transmission. For this project, it is important to understand at a high level how we can manipulate images through code. Using a programming environment like MATLAB, we can import the image and break it down into a matrix of pixels, with each entry in the matrix having a red, green, and a blue component. These components are in the range 0 to 255, with only integers allowed. This is commonly called the pixel's RGB value. Sometimes this is stored in three separate matrices, one for red, one for green, and one for the blue values. There are different formats for storing images on a computer, and sometimes other values are included, but for this project, the important thing to know about is a pixel's RGB value. Once we have these pixel values, we can permute and change them in any way, and then reform them into a new image. For example, we could replace the top row of pixels of an image with the values 255, 0, 0, with 255 representing the red component and the two zeros representing the green and blue components. Then we could reform the image from its RGB values, and we would have the original image, but this time with a red bar on top. For this project, we want to use chaotic data to modify an image in a way that hides the original image, but makes it possible for a designated receiver to revert the image to its original state.
We will now show an implementation of encrypting and decrypting an image file using the driving and receiving system framework. We start with the image airplane from the University of Southern California. This image has dimensions of 512 by 512 pixels, and each pixel holds 3 values, the red, the blue, and the green color components. When the image is read into MATLAB, it is stored as a 512 by 512 by 3 array. We take the RGB values of the first pixel in the image, 107, 32, and 91, and use these as the initial conditions of the Lorentz driving system to generate a chaotic solution X. This is the MATLAB code that accomplishes this. The image is first read in and displayed, values for calling ODE45 are set up, the initial conditions are obtained from the first pixel's color values, and the chaotic solution is generated by calling ODE45. Something important to note is that the number of time steps and the length of the chaotic solution are equal to the number of total pixels in the image. When we add the chaotic solution, or masking, to the original image's color values, we want the masking to have a significant effect. To accomplish this, we scale the chaotic masking by a factor of 60, round the chaotic masking so that it is only integers, and then send that plus the original image's color values as a sum to the receiver. This is the MATLAB implementation, where the chaotic masking is scaled by 60, rounded, and then added to the original image's color values. The A2 matrix is sent to the receiver along with the X component of the driving system. If we mod the A2 matrix element-wise by 256, so its values fall between 0 and 255, we can produce the signal sent to the receiver. The effect of the chaotic masking is significant, and the original image is completely indiscernible. The receiver receives the sum of the chaotic masking and the original image's color values, and they run the receiving Lorentz system using the X component sent from the driving system, which synchronizes to the chaotic masking. This masking can then be scaled by 60, rounded, and subtracted from the received signal to recover the original image with a small error. The function that I used to accomplish this with ODE45 was evolving the driving and receiving systems simultaneously, or synchronously, although it could be implemented as 2 separate ODE45 calls and produce the same result. The first 3 components of the Y vector are the X, Y, and Z components of the driving system, and the last 2 components of the Y vector are the Y and Z components of the receiving system. This is the MATLAB implementation of subtracting off the masking from the received signal. Once we have the recovered original image, we can display it, and it looks just like the original image. It is difficult to tell any difference between this and the original. If we zoom into the top row of the image, we can see where the error due to synchronization occurs, and this synchronization happens extremely quickly, as only the first row of pixels are distorted.
Another application of chaotic encryption is masking audio. As an example, we'll walk through the encryption and decryption of a song snippet. First, we read the audio into MATLAB, where it is stored in an n-row by 2-column matrix. Here, these are represented by the matrix A containing the 2-column vectors L and R. There are 2 column vectors because each one represents a single channel of audio, and this audio snippet has 2 channels since it's a stereo recording. The length of these column vectors depends on the length and sample rate of the audio snippet. In this specific case, the column vectors are of length about 1.2 million. We now solve the coupled Lorentz equations in order to generate chaotic data. We choose initial conditions based on the first non-zero part of the audio, but we can use any initial conditions and everything should work out in a similar way. The code here on the right simply shows what was just described. One important factor is to make the t-span at least as large as the column vectors, so there is enough chaotic data to mask the entire snippet. This is the MATLAB implementation of the coupled Lorentz equations we are solving for this example. The first 3 functions make up the driver system, and the 4th and 5th make up the receiving system. Note how the receiving system depends upon the driving system, with its use of the y1 state variable. Now that we have the chaotic data, we can move on to actually masking the audio snippet. We add the chaotic results from YD and ZD on top of the original audio, using YD to mask the first channel and ZD to mask the second channel. In the notation from the previous slide, we are adding YD to L and ZD to R. MATLAB stores the audio data in numbers from the range -1 to 1. So, in order to be able to play the masked audio for this demonstration, we rescale it to be in that range. That is what it's seen in the code on the right, with song 2 being the unscaled masked data and song 3 being the scaled masked data. Here is the snippet of the masked audio. To decrypt the audio, we can use the chaotic data from the receiving system to remove the mask. We subtract YR and ZR from the masked and unscaled audio data, which should leave us with the original audio sample. This shows the coupling in our dynamical system. We are able to remove the noise generated by the driver system with the noise generated by the receiving system. Here is a snippet of the unmasked audio. This is a plot of the first 0.03 seconds of the unmasked audio. I changed the initial conditions slightly to make the noise at the start more apparent and easier to plot. Also, this plot represents a part of the audio not played before because it is just silence. However, because it is just silence, we know that the correct audio should be just a flat line at 0. We can see some noise for the first 0.015 seconds, but after all that, the noise is removed and we are left with just the horizontal line at 0. This shows how fast the convergence of the receiving system to the driving system occurs. In this example, it only takes about 1/100th of a second. One last thing I'd like to add is that this whole example has been asynchronous, but it should be possible to make something similar work in real time as well. The sender and receiver could agree on initial conditions for a chaotic system and both generate chaotic data. Then the sender could send the masked audio over something like a phone call, and the receiver could use some sort of method to unmask only the chaotic part of the sender's audio and then hear their unmasked audio in real time, which I think is pretty cool.
To summarize, we've seen that the driving and receiving system framework can be used to encrypt and decrypt information. We've also seen some of the conditions for synchronization to occur in coupled chaotic systems. From here, we can implement more robust counterattack measures for this project to improve security. And that's the end of our project. Thank you for listening, and we hope you enjoyed.